it's always a plus. So basically, we're going to go through a presentation of the project, description of the system, order expectations, system selected, energy savings, super subcritical and transcritical cycle, heat reclaim possibility, and factual energy management. So basically, the case, what it is, it's a reading Pennsylvania, the Santander Arena, which is the home of the Reading Royals in the HCHL East Coast Hockey League. For us, it was a very, very important adventure because it was the first time in U.S. and even in North America that we were going to do a project in a major stadium. And what I mean by major stadium, this is 15,000 seat stadium. We've done a lot of them, but that was by far the biggest. The original system was from 2001. It is an R22 system that has been serving the ice rink facility, and it was coming to the end of life. So of course, everybody know about the phase down of R22. So for them, it was something that was really, really, really crucial into their operation to move from R22 system to something that was going to be a long-term solution and hopefully future-proof. So if we look at some of the picture of the system, and I know they're not really good ones, sometimes it's not easy to be well positioned. So basically, for us, it was a standard R22 system with two reciprocating machines running on low speed, belt driven. You can see, I don't know, can I use a pointer? Not really. You can see in the back of one of the picture, you can see the middle picture, excuse me. You can see the compressor, you can see in the back the chiller. On your right, it was connected on the discharge side, excuse me, to an evaporative condenser. And on the left, it was the electrical panel. On the next picture, you have a little bit of a better view of the existing system. So the room was pretty tight, and we don't even see the floor pump and the evap condenser pump. That was strictly the package that you can see. And again, in the back of the compressor, you can see the Chanzu flooded chiller. So for those of you that do not have any knowledge on flooded chiller, this system that was 150 to 160 ton package at running condition for ice rink system, the flooded chiller is about 1,800 pounds of R22 in the system, without even considering the charge which is in the evap condenser. So you can imagine that losing the entire charge of the system and trying to replace it with R22 would have been a big challenge. First, finding the R22, and secondly, the price tag that would come with that would have been like quite a challenge. If we look at the ASHRAE recommendation in terms of end-of-life equipment, you can see that the floor is normally about 50 years that we can expect out of the floor. The headers would be 25 years, chiller 20 to 24 years, compressor 20 years, evap condenser 20 years. Again, from the ASHRAE table, but normally if you go through 15 years on an evap condenser, especially if you don't treat the water correctly, you would be lucky. So basically it was like the perfect storm for them. R22 system, end-of-life system, they needed to do something. So if we move to the, basically the expectation of the customer, the management was really, really, really focused on four things. The very first thing was energy efficiency. The second thing that might seem a little bit surprising, they wanted to reduce their water consumption. The third thing was they wanted a system for 30-year life cycle. And finally, they wanted a low maintenance cost. So ASM Global, which is the owner of this facility that has facilities all over North America, were behind that. And for them, they were considering many approach. And CO2 was in line, but they were having some, I wouldn't say some fear, but they had some doubt since it has never been done in a major stadium. Considering every option and keeping in mind the four major criteria that they have, we look at almost every way we could do it. we finally selected a transcritical CO2 system. Excuse me, I just want to make sure I didn't miss any slide. So for those of you that knows an industrial R22 system, and we are moving to a CO2 transcritical system, if you have a look at it, it's not really different. We have a compressor, or we have many compressors. We have a chiller, we have a condenser, and we also have a pressure reducing valve. The only difference, and if you look at this diagram, you can see that the outlet of the gas cooler is going into a flash tank. And this is probably the biggest difference in a system, in a CO2 system compared to any other system. In this case, we're going in there in indirect with the glycol in the floor. We're already using glycol, and we kept the same floor, and we kept glycol in the floor. Now, how do you make such a selection? How can you predict what would be a good system? What would be the outcome? Normally, when we spend a lot of time trying to have energy measure, trying to figure it out, what would be the energy consumption of such a plant, we have some experience. We can use some tools, we can use Excel, we can use some software. When we are trying to compare a CO2 system, it could be a little bit difficult, and it could be really, really tricky. And I'll come for about it like in a few seconds, but I've been using, in this case, I've been using a software from Europe, which is called APPAREL calculation, which is basically you're building a load profile. It might not be the exact load profile of the facility, but you're building a load profile, and then you compare every refrigeration system against the same load profile, and it's going to give you an energy performance. I'm not saying it's a perfect tool, but at least it's something that we can use to have an idea of what it's going to be. In this case, after building the energy load profile, it came out to be that compared to the R22 existing equipment, we were predicting an energy reduction of 19% using a CO2 transcritical versus the existing R22 system. The ammonia was going to be 12% lower, but in this case, using an ammonia system was not possible because of the mechanical room location. So the customer really went for the CO2 system. Now I'm going to go into a little bit of theory for a few seconds, just to make sure that we are all on the same track, to really understand. When we're doing refrigeration, and I think this is called a pH diagram, well, from what I remember, we always have like the evaporation, compression, condensation, and expansion. Same thing with any refrigerant. Nothing really special. We can calculate the COP, we can calculate the size of the compressor, we can figure out the size of the equipment, and this is basic thermodynamic 101. When we are moving to a CO2 system, now we're getting into some different kind of thinking. And when I'm saying that, it's not really different, but it is different. We are using CO2 system in a subcritical mode, which is exactly what I presented the previous slide. And sometimes it becomes a transcritical mode. What does that mean? That means that we have the pH curve in the blue form, and then we have the vapor curve below the green line, and then we have a super gas over and above the green line, and then we have the liquid left on the yellow line. And when we are above the red line, we are into the subcritical mode. What does that mean? Am I going too fast? Everything's okay? What does that mean? Well, a lot of time, again, when we are comparing one system against another, we have a static picture. You look at the R22 system, you look at the pH diagram, and it's going to give you the COP or the kilowatt consumption of the compressor. You do the same thing with a CO2 system, and you're trying to see what is the picture, and then you're trying to figure out what would be the energy consumption. Again, looking at this is another software from the same company or from the same amount of people that build that software. This one is called Simple CO2. You can find it on the internet. It's pretty nice. It's pretty simple. It's really fun to use it. And if you look at the pH diagram, that would be a CO2 subcritical cycle. And I'm not going to look at all the number, but there's one thing I would like to get your attention. If you look at the COP, which is like middle left of that graph, you're going to see 4.69. So if you're running a CO2 system under those conditions, you're going to get a COP of 4.69. Now, I don't know if you ever run an R22 with ammonia or a synthetic refrigerant pH diagram like that. What would be the range of the COP? It would be anywhere from 2.6 to 3 point something. Now, something else which is important, and then I'm going to switch to the other chart. If we start using a CO2 system under a transcritical mode, what is happening? Well, there's a lot of things happening in the system, but basically, when people look at the same pH diagram, entering different running conditions and looking at the COP of that system, again, at the same place, you can see that the COP is 1.7. And you're wondering what happened. And sadly, and I would say really sadly, a lot of time when people are considering a CO2 system, they're looking at a static pressure, a static picture, which is that one. And they're saying, you know what? Your CO2 system is not performing, and you're not going to save any energy, you're not going to save any money. But this is a static picture. This is running in the worst day of the year. Now the question that we should ask, how many days of the year are we running under those conditions? And how many other days, and I'll go back to the previous slide, am I going to be running under subcritical mode? And this is where it makes a difference. And sometimes it does take time to put all those equations in line and figure it out what would be the overall performance of a CO2 system. Now if we keep moving, I'm going to a third slide. I'm still running under transcritical mode. And you look at the COP, what did happen? I'm at 2.61. So what is the difference between this one and this one? I'm going to go slow. This one and this one. We can see that the line at the outlet of the condenser going to the flash tank is further on the left. What does that mean? First, when we are running transcritical, we're no longer condensing. We're moving from high pressure gas, high temperature, and we are cooling it down, and it's still a gas. This is when we are over and above the pH diagram. Colder the temperature going to be outside, colder the outlet of the gas cooler is going to be. So again, we're going to look at those two slides. What's happening between this one and this one? It's only the outlet temperature of the gas cooler. Colder it's going to be, I'm going to get left, 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 and left. And when I'm moving left with that vertical line, I'm creating less flash gas. If I'm creating less flash gas, I'm more efficient. If I'm more efficient, my COP is going up. This is what happened with a CO2 system. And again, it took me quite a long period of time to really understand the entire dynamic of this. Many, many years ago, when I started getting interested into CO2 system, a manufacturer in Europe published that chart on the left. And everything that was red, basically it was saying, if you are within this area, you're not going to be really performing compared to any other refrigerant. That was 15 years ago. Now with technological development, people keep on thinking, how can we do things better? Developing new equipment, developing new approach, new technology, and I'm going to name some of those like parallel compression, ejector, adiabatic condenser. Right now, I don't have this map as it is today, but I can tell you that there's almost no more red on that map. Now if I come back next graphic on the right, remember what we were projecting on the energy simulation? We were thinking that we're going to get 19% reduction versus the existing system. If you keep thinking about it, when we are under a CO2 transcritical mode, remember when I said that when we are in transcritical, we are no longer condensing? So we're going from a very warm gas and we're cooling it down. So it also changed the dynamic in terms of heat reclaim. We have discharge temperature sometimes close to 300 degrees Fahrenheit. And we keep going down, 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 and as low as possible. So that means that we can have various heat exchanger along the way, and we can take advantage from that high discharge temperature going down to actually warm up something else that could be used in the building. In this case, we can see the temperature versus enthalpy graphic, and you can see that the red line is going to be high temperature heat recovery. Then HX2 will be low grade heat, anywhere from 80 degrees to 100 Fahrenheit. And then finally, the last heat exchanger would be the gas cooler, injecting the remainder of the heat outside. We can play with those heat exchangers, but another thing that you can keep into consideration, when you're gas cooling versus condensing, your temperature keeps changing. So that means at the beginning of the heat exchanger, your gradient in temperature is way higher than when you are condensing at a fixed temperature. That means that I can have a gas cooler which is selected at 5 degrees above outside temperature. I can still have a decent sized condenser when I'm doing that. Now the other thing which is really interesting, when you are playing into the transcritical mode, and funnily, you can play with the pressure. Pressure and temperature are independent. Compared to when you are condensing, pressure and temperature are the same. When you are over and above the curve, in some occasion, you can push the pressure, and this is very surprising. You push the pressure, and you end up sometimes with a better COP. What did I just say? Normally, when we do refrigeration, we're trying to have the compressor as close as possible. Highest suction temperature, lowest condensing temperature, and then we have the highest COP. On CO2, we're running transcritical. Sometimes I push the pressure just a little bit more, and I'm getting a better COP. Why is that? If you look at the temperature curve, which are the black one, just the shape that they have, if you go higher up and you look at the shape of the curve, you're going to end up further on the left, creating less flash gas, and as soon as you have less flash gas, you improve the COP. The other thing which is really nice, when you're playing with the pressure, you're also playing with the amount of heat of rejection, you're playing with the quality of the heat of rejection in terms of percentage. Higher the pressure is going to be, more high temperature heat reclaim I'm going to have. Then it's a question of how much do I need, and where do I want to put the pressure to make sure I have the most efficient COP. Now, let's get into the real number. We started the plant, everything was nice and easy. It went really, really well. We went right in summertime at the end of the season, and we needed to be ready for the start of the next season. The very first month, start running. Then on the second month, we asked the customer, can we see your energy bill? We were as eager as they were to see the result. Well, the very first bill, which is right there, and you can see like bottom left, that the previous year, it was 465,000 kilowatt hour, and the very first time they used the CO2 transcritical system, it was 289,000 kilowatt hour. And this is the real invoice. We put on a graph the entire energy consumption throughout the entire season. And then we also put another graph where we were comparing the previous operation, full season operation using R22 versus using the CO2 transcritical system. It turned out to be, over the course of the entire season, 55% reduction in energy by April 2023. We predicted 19% improvement. We ended up 55%. reduction. Why is that so? Because we're taking advantage of the change in outdoor temperature and try to always maximum the COP of the system. Now we went from an evaporative condenser on the roof and we went with a gas cooler, adiabatic gas cooler on the roof. Total saving was 1.1 million kilowatt hour over the span of 6 months. Now this is the package when we worked pretty hard to get it in the mechanical room, I can tell you that. That was not easy. Once it was inside the mechanical room, this is what a CO2 transcritical package looks like. Now, if we look at the roof, we went from an evaporative condenser, we went to an adiabatic gas cooler that was sitting right next to the cooling tower of the entire facility. They're still using cooling tower for their air conditioning. Now, another very impressive result, we start measuring, or the customers start measuring, and was getting the bill from the water supplier as well. We noticed another saving of 55.23% in water consumption. We went from 500,000 gallons in a season to 228. So basically, we achieved everything that the customer was expecting. So in order to finish that, in conclusion, you can see some of the client testimonial. So the general manager, at the end of the day, the financials are our lifeblood. What we had before, we just an energy guzzler. From a usage standpoint, we are using only 50% a month versus last year. Some of the players were saying the ice is fantastic. This one I don't understand because it's the same floor. We didn't change the floor. I'm glad they're saying that. The only thing I can think of, the CO2 system probably is picking up the heat load faster than what the R22 was doing. Some of the material I used for this presentation, the chart was coming from Danfoss. The energy calculator was coming from IPU and Danish Institute of Technology. Same thing with a simple CO2 software. Of course, the energy supplier was Constellation, Pennsylvania. And you can see at the bottom 2 links that if you want to go have a look. The first one was the CO2 mentor that presented the entire commissioning of the system. And the other one is a little bit of marketing material coming from us. Thank you very much for your attention, and it was a pleasure to present that case study to you. Thank you.
We'll take the question at the end of the conference, so please note your question. The next presentation will be done by Dr. APPAREL Langer-Pontana. He is a distinguished professional engineer with over 45 years of experience. He has been actively involved in ASHRAE Technical Committee and is a distinguished lecturer. Dr. Langer-Pontana has held several leadership positions, including the 2019-2022 Society Board of Directors and the current Regional Vice Chair for the Membership Promotion, RVCMP, of the Certification Committee of Thailand Region 21-24. He is also a valuable contributor to the subcommittee of the Council Engineer in Thailand and served as an advisor at the Thai Society of Mechanical Engineers. Please welcome Dr. APPAREL.
Good afternoon, everyone. So then I would like to start for my presentation for the CO2 in the subcritical, mostly in the ammonia and cascade system. So the enterprise system different between the CO2 and another refrigerant, and explain the effect of pressure loss for the greenhouse emission of CO2 and understand how the refrigeration system efficiency very different CO2 system and cascade system. Understand the difference between standard high state and booster system versus the CO2 and ammonia cascade system. And due to the phase out of the CFC and ZFC, so the more and more we will consider to use the CO2. So the objective, we learn the CO2 system, and then we learn what is gas emission and understand. And we also have to submit the new innovation of the fanless vacuum condenser. And you can either to be the adiabatic fanless vacuum condenser too. And learn the exchange defrost system with the variable feed pitch and the EUI measurement optical per pallet. And as we know the formal refrigerant like the HCFC today and all the HFC today, we will phase out soon too, because just only interim. You can see that the also global warming, they have about 1300 of the GWP for the R134A, and the R507A is acetate. The refrigerant is 3800, and the ammonia is less than 1, and the CO2 is baseline is 1. So anything is higher than 1, we call a global warming. And I just show you how the cascade system works in the graphic way.
Cascade system is the most advanced one, and these systems can become very complex. It's suitable for refrigeration systems which require different temperature ranges for their cooling loads, and also makes it easier and cheaper to comply with health, safety, and environmental regulations. These refrigeration systems usually consist of one or more separate refrigeration circuits, often using different refrigerants to provide a cooling effect. In this system, we have two compressors, except they are both circulating refrigerant around separated circuits, a high temperature circuit and a low temperature circuit. Connecting the two circuits is a heat exchanger known as a cascade condenser. This acts as a condenser.
Yeah, that's a simple cascade system. So between the two state and cascade, the two states system is one single refrigerant, and the cascade system is two different refrigerant. Is a high state, maybe one refrigerant, the other booster system have another refrigerant that they call cascade system.
Cascade system is
So this also the one that I will use as the case study. They have the one that ASRS ammonia and CO2 room. It's a quite large storage room. It's about 18,000 pallets together, and then the system, you can see that they have a booster at the reciprocating compressor, and the high state is a screw compressor, and run together with this one is a family vacuum condenser. So we just show the LED running around